moment. All right, so what I want to do today is wrap up the discussion about fault tolerance. I mean, it's worth discussing, but at some point you have to give up and move on. I'm not trying to exhaust the topic. It's impossible to exhaust any of these topics. There's no such thing as exhausting the topics, actually. It keeps on going on and on. Many research papers and whatnot. Okay. What I do want to talk about is this extremely important issue that we started last time, namely two-phase commit. Now, two-phase commit plays an extremely important role in distributed systems. It's one of the most recognized core algorithms for achieving some sort of consensus while running transactions. Now, let me warn you from the beginning. Two-phase commit is going to have some problems. We are going to discuss in great detail two-phase commit. It has some problems. Solutions have been proposed. One of them is three-phase commit. Three-phase commit is extremely talked about, but virtually never implemented algorithm. Okay. It tries to solve a problem that does exist, but it's rare in two-phase commit. Since that problem, with a little bit of care, will result only in a performance penalty for two-phase commit rather than incorrectness. Essentially means that yes, you want to mention it, you want to talk about it, you want to show how you could fix the problem, but because it's going to require another wave of messages on top of two-phase commit, is almost never worth it, right? So this is one thing that you have to pay attention to, namely some sort of evaluation with respect to what's the real price. So what I want you to keep in mind is the following situation. Imagine that I lose a second when the algorithm runs amok, right? For example, in two-phase commit. So, well, a second can be really bad because I might be able to run thousands of transactions in a second, okay? But imagine that that only happens once every year. Alternative to this is to make sure that I never lose that 1 second, but I for example, increase the number of total messages by 50%. So when it comes to trading off an incremental cost that's attached to everything versus a one-time cost that could be quite large, worth thousands of transactions, let's say, but it happens relatively rarely, well, I mean, you have to seriously consider paying the one price every now and then when it happens versus incremental cost that gets spread all over the place, right? Unless you have a relatively high failure rate. For example, 1 in 1,000 transactions runs in trouble. It's not worth really avoiding paying the occasional cost. Okay. And I mentioned this, things tend to be quite reliable. I mean, okay, another thing I don't want you to believe it's happening. The fact that we talk about fault tolerance all over the place and we make a very big deal out of it, it doesn't mean that these systems are so unreliable they keep on dying. Now that is happening, for example, with sensor networks because of the flakiness of the system. But it's really not happening with any other modern computer system. And these systems don't just go up and down and up and down and up and down, right? I have servers that stayed up for a year until the whole power in the whole university went down, literally, right? So don't get the feeling that it's some sort of Armageddon and we have to all the time deal with all of these failures. So this is why optimistic approaches might be better, and the two-phase commit is really an optimistic approach, than slightly pessimistic but pay a higher price to keep on going. Okay. All right. So let's talk about two-phase commit. And I'm going to weave two stories here. One of them is what happens from a distributed system point of view, and another one is what happens from a system point of view with respect to its own failures and how to recover from them. It turns out that you must be able to recover from your own failures in a transaction-friendly way, because if you can't do that, then you're in completely different kind of trouble. Okay? But luckily, that problem is well understood because of the database community, and something called a log can actually be used to do this. Very similar to the kind of log you have, by the way, for the Project 4, Part 1. Okay. So those logs can allow you not only to debug, but can allow you to, in fact, recover state. And I'll mention a little bit about what goes on in there. Okay, so let's look at the two-phase commit, and let's see what the goal is. So the goal overall is the following. So I have a number of processes independently. They were doing the processing of the transaction. They essentially run the same transaction. The goal is to do the same thing at multiple sites so that you have redundancy, right? So if one side goes down, I have redundancy, and the other sides know that something happened. Now, we are talking about redundancy that even goes beyond, okay, if I crash, I recover and I come back. We are talking about redundancy in the sense that even if one of the sites gets completely destroyed, flood, for example, would completely destroy things, or fire, right? You still know that you've done the transaction. Think financial transactions, for example, where you really don't want to lose the fact that a particular money exchange has happened, even if there is flooding in an area, okay? I mean, why? Well, because usually you have riots associated with money losing, right? So, I mean, you get into social issues if you don't carefully keep track of money. Now, if you lose people's emails, it's not such a big tragedy. If you lose people's money, then you're up for a big surprise. Okay, so we have independently running transactions at multiple sites. They run effectively the same transaction. Independently, they will decide whether the transaction goes to a commit or an abort at each of the different sites, depending on what goes on that machine. And these systems are complex. You can't make them do exactly the same thing, right? I mentioned this, that there are many reasons to abort a transaction. One of them is literally you detected some kind of a defect when you were running it, and to recover a correct state locally, you have to abort, okay? Now, the trick is to take all of that combination of commits and aborts that happened at each independent site and to do a global commit or a global abort. Now, obviously, you can only commit globally in principle if all the sites decided to commit. But think that that's, in fact, the optimistic situation that happens most of the time, okay? So what we need is some sort of a protocol that allows these multiple sites to propagate the knowledge that they all agree to commit so that they can actually commit. Now, the easy way out is to abort. I want you to understand that. But an abort is costly. So if you abort, that's a safe decision from the point of view of the transaction processing, but essentially means you have to go and do again whatever is it that you're doing. So whatever client issued the request, when it sees the abort, it will reissue the thing. Because, I mean, otherwise you can say the safest way to do e-commerce is not to do e-commerce. It's not exact. I mean, it's true. It is the safest way to do e-commerce, but that doesn't help at all, right? So there are these two things that need to be kept in balance. We do need to make some sort of a progress and have a reasonable performance for the system. So we do want to see a healthy amount of commits going on. But at the same time, we need to be safe. And quite often, being safe means abort when unsure, okay? So let's see, how could we pull off this kind of okay, we all ran. We know what our decision is, but we have to achieve some kind of a global consensus whether we commit or we abort, okay? Now, I want you to keep in mind that a commit, either a commit or abort, are, in fact, strong promises. If you say commit, right? I mean, if the global decision is commit, everybody agrees that you commit, which means it doesn't matter what happens with any other systems, things go down, flooding, or whatever, right? After some recovery, which is allowed, you know that you committed, and the state of the system reflects the fact that you committed. If it's an abort, the state reflects that it was an abort, i.e., it wasn't touched at all, okay? So I'm going to assume from this protocol that each machine has the ability to correctly abort or commit, even in the presence of crashes. How that happens, you pretty much have to take a database class to see how a database could do this. But we're going to have a little bit of a discussion, but it's mostly related to the use of something called a log, okay? So it's a very specific technique, highly studied in the database literature. Essentially, you're writing on permanent storage what is it that you're about to do, and that allows you to correctly recover the state, even if you crash, okay? It's not trivial, and it's in fact quite hard, but it's possible. All right, so let's see how this is going to work. Now, both the two-phase commit and three-phase commit need a global coordinator. Again, how do you get a global coordinator? With some sort of a leader election algorithm. Okay, so assume that we have a leader election algorithm. All the machines that are still reasonably healthy have decided that this specific machine is going to be the coordinator, which, I mean, the coordinator itself might have its own transactions or not. Even if it does, it has to run both as a coordinator and as a normal process. Okay, so I have two pictures here. The first one is a state transition diagram for the coordinator, and the other one is the state transition. I'm sorry, this is, the coordinator, and this is for a participant. Okay? Now, all of them start into some kind of an init state. And in between the init and something else, they are doing something with the transaction, namely making up their mind if they want to abort or commit, except, of course, the coordinator, which I'm going to assume it doesn't run any transaction. The coordinator will just coordinate the act of figuring out if we commit or abort. Even if the coordinator machine does something, you simply have these two separate pieces of code that run the coordinator code and the participant code. Okay? So from the point of view of the coordinator, you start in an init state, and in the init state, you're going to send a global vote request. So this is effectively some sort of a voting algorithm. Okay. You send the vote request, and from the point of view of the coordinator, here is what you would like to see happening, right? You need to you know who the participants are, and this is crucial. So you have a very clear notion of group membership, right? So ingredients for this algorithm is we have group membership, and we know exactly who's in the group, and we have election within the group, and we know who's the coordinator. Okay. Now the coordinator will in fact wait and keep on staying in this wait state. Will in fact wait for a reply from all the participants. And it can get 2 replies from the participants. Each participant can say, but it can take a while until they do this. Each participant can say either commit or abort, okay? Depending on what happens from the point of view of running the transactions on the participant side, okay? If you get a single abort, you have to abort the entire thing, right? So a single abort while being in a state wait will mean send some kind of a global abort. If you got a commit from absolutely all the participants, you send a global commit. So both the vote request, global abort, and global commit are in fact multicasts. All right? You can use any mechanism for the multicast itself. So you send the vote request to everybody, you send the global abort if needed to everybody, and the global commit to everybody. Now how you implement this multicast, right? Again, you might have support in the network fabric if it supports multicast, which it makes it probably a little bit better, or you might use separate unicast to send the multicast. In either case, it doesn't matter. So unless you have a reliable multicast, right, you have to be worried about the multicast not making it completely through. I mean, it makes it to some participants and not to some other participants. We're going to view the discussion in 1 minute or 2. Okay. Now let's see what happens from the point of view of a participant. And I mean, the important thing is not how things could go right, but how things could go wrong. Okay. So let's see first how things could go right, and then we see how things could go wrong. So as a participant, you're in the init state, right? And during the init state, you do or you don't do your transaction. At some point, you're going to get the vote request coming from the big coordinator. When you're in the, right? When you're in the vote request, when you get the vote request, you get into a ready state and immediately send a message to the coordinator with your vote. Okay? Your vote, again, can be an abort or a commit. Right? Now, of course, if your vote is abort, you could even go ahead and abort your transaction, because you know that if your vote is abort and your voice, I mean, even if the protocol only later sends the abort, right? Aborts are always safe, by the way, because if you vote abort, you know everybody has to abort. So you might as well go do the abort. But if you vote commit, you cannot go and commit. I want you to understand this, because it's not clear that somebody else did not fail the transaction. So you get in the ready state, you send your vote to the coordinator, and then you wait. You wait for either a global abort or a global commit, right? So the way this is going to work is you send this vote request. These guys make the transition, depending on how they run transactions and so on, into the ready state. Only when everybody reaches the ready state, all the messages make it back to the coordinator, and one of these messages goes through, these guys can make progress. And of course, they are going to make progress independently, right? So there is some sort of a barrier happening in there. Now, they can go and abort and commit independently of each other once they got the global abort and the global commit, right? And they don't need to do any other extra coordination. So the trouble is, there are 2 points in which the whole process can block. And if something goes wrong, that could block indefinitely, and that's the main issue. So the coordinator can block on wait. I mean, it sent a message, but it simply did not get all the replies. So how can that happen? Well, one of the participants, for example, is crashed. If it's crashed, it might not send the reply. Then what? I mean, if it's crashed forever, it never sends the reply, and that's really bad. Okay? But the same kind of blocking happens here. You got the vote request, you send your vote, but you stay in the ready state, and you wait either for a global abort and global commit. Now, what could happen is the global coordinator died, right? And if the global coordinator dies, none of these messages comes through, and you have the transaction suspended. Now, we have to start to throw in some of the mechanisms we already know of. in order to prevent against this, it crashed and nobody knows that it crashed. Okay, so what's one of the ways to do this? Well, timeouts. So you're going to say, you know what, let's add timeouts to the entire process and essentially make sure that if we don't get something back within a certain amount of time, we know what to do. Again, the know what to do is the abort. So you see, if nobody hears from anybody else, the only safe thing to do is abort. The unsafe thing is always commit, right? If you abort, as long as at any moment of time you make everybody else aware that you aborted and nobody is allowed to commit unless that you all know that you committed, it's always safe to abort, right? So then you can have timeouts and you can say, okay, I made the transition from init to ready, but if I don't get the global abort or the global commit, I could decide, for example, to abort. The same thing can happen here, right? The global coordinator is going to send the multicast. If it doesn't hear from the participants within a certain amount of time, it's going to say, okay, let's abort. Okay? But you can still run in trouble. And that's the big problem because of the following situation. Okay? This guy makes it through. So this is what I mean by there is a rare situation that can happen, and then we'll wreak havoc on this kind of a thing. So the problem is the following, actually. Assume you don't have a multicast that's a reliable multicast, so that's an all or nothing, and you know it got delivered. Okay. So everybody makes progress, right? The init, it goes into the wait. This guy's going into ready. They send their acknowledgements. And this guy gets all the acknowledgements and starts to run the multicast. And it sends I mean, if it sends abort, it's not a problem, because, again, you can safely abort. But if it sends the vote commit, but not to all the participants here, okay? So some of them get it, in which case they say, hey, I got the global commit, I'm going to commit it. But some of them don't get it, and they are stuck in the ready state. Then what? So this is why, for example, for this possibility, this guy cannot abort just in case. So you see, if they have an abort themselves, they know that there is no way the whole thing is going to go, and they abort. But if they have a commit, they cannot actually abort in this protocol once they make it into the ready state. Just in case the coordinator sends some of those global commits, but the global commit didn't make it to this guy. Okay? Now, the moment you notice something like this in this protocol, you start to think about, hey, maybe I could fix some of these problems. And how could you fix some of these problems? Well, you can fix them by saying, I know how to tell the difference of whether there was, I mean, as long as you find the decision, whether it was a global commit or a global abort, right? You can just go and implement it and you're safe. It doesn't even matter if you do it at the same time, right? So then, on a timeout, you can say, I'm going to try to contact the other participants into the protocol and ask them, did you ever see a global abort on this transaction or a global commit? If any participant saw a global commit, it is a commit. You agree? It's just the global commit didn't make it to all of them, but the coordinator decided to do a global commit, and it actually sent the message. Okay? Of course, if they see an abort, they can actually abort. But there is still this possibility that this guy decided to commit, but didn't manage to send commit to any of the participants. Now, there is this intertwining now that we have to pay attention to between crash recovery that has to be implemented in order to run transactions in the first place, crash recovery on each of the sites, and what could happen if you correctly recover from the state, okay, if you correctly recover from the crash. Right? In order to do crash recovery, each of these sites is going to use a log and will, in fact, correctly determine the fact that they took a certain decision and try to replay it again in order to make sure the protocol goes. Right? So the danger there is that this guy, if it crashed just at the right moment, he can still send a global commit. And these guys decided to do an abort, but not all of them get to do the abort. Right? So there's this tiny, tiny window now in which things can still run amok. Okay? Another problem is the fact that to make that safe, you can actually do the following thing. You can, to be on the safe side, you can wait in the ready state until the global coordinator fully recovers. So you transform a problem into a performance penalty, right? So if things go right, they go right. But if they go wrong and this guy dies, you might actually have to wait. If nobody actually got a global commit and right? And these guys can actually say, could we commit or could we not commit? They, in fact, have to wait for this guy to recover. So the whole transaction mechanism is now stalled because this guy does not go through and finish the commit. Now, they cannot even elect another leader until this guy recovers. I mean, they can, but they cannot finish that specific transaction, okay? Right. Now, how fast could you recover from such errors? Well, I mean, it depends on the specific mechanism used with the log and so on. But if it's a complete machine crash, for example, it could even be tens of minutes. But again, if it happens only once a year, that might actually be perfectly acceptable, right? So there is this trade-off that needs to be done there. Is that hiccup going to hurt me if it happens relatively rarely? Now, of course, if you crash once every hour, it's a complete disaster, and you better do something else, in particular the free phase commit, right? So this is basically just a table that summarizes the same thing. This is the state of the coordinator, and this is the action of the participant, right? If it was commit, you have to commit. If it's abort, you have to abort. If you are still in it, you can abort. I mean, this is the nice thing, right? And if you're in the ready state, you have to contact this other participant, is what I just said, to try to figure out what to do. And in a rare situation, you have to wait for the coordinator. Okay. Now, let's go into some details and see exactly how the logging could be intertwined into the protocol. So it turns out that logging, it's a very tricky business, and you cannot just do log. I mean, logging refers to the fact that you're going to write something in a file, let's say. It's a very special kind of file, and it must have special properties. I'm going to mention some of them right now. In particular, it has to be on stable storage. That means it's actually a very strict requirement. That essentially means that when you write something into that file, you have to make sure that it makes it all the way to the disk. Because if it doesn't and you crash in the middle, you lost entries into the log, and it's hard to say what you lost and what you didn't lose, right? So the log itself, it has to be a special facility. It's very special because even file systems are going to cache all kinds of things in the way and so on and try to improve performance, and that's really bad for the log. So the implementation of the log has to be done very deep into the operating system. I mean, you have to use a facility that, for example, doesn't use any kind of buffering to control how it goes, right? Usually, for example, a large database installation is going to use separate hard drives just for the log, right? So, for example, a typical scenario is use about 20 hard drives to store the database, but use 5 super fast, very expensive hard drives to store the log. And you have to be able to write in the log very fast, because essentially what you're going to write in the log is every single thing that you're doing, right? Some of the logging, for example, even contains the information that is needed to fully play back again the complete transaction, all the changes that you would have done to the log. It's not only the intention. So you can log metadata, or you can log everything. For example, if you change the value of for example, one of the fields in the database, you can write in the log, I'm changing the value. And depending on which type of log it is, you might say, this was the old value and this is the new value, or just write the new value or the old value. These are called redo, undo, and undo, redo kind of logs, right? So these logs can actually get quite sizable, okay? Now, the log itself is not needed in the normal functioning of the database. It's only used in the recovery process, right? So what I want you to take out of this is, there is this tricky business of recovery on a single site, and database community dealt with it. In the database class, I do talk about that. And then there is the tricky business of running things in parallel. So let's see a little bit how, part of what needs to be put in the log, it's activities you do now even as participating into this distributed commit, right? So if you run a transaction on a single site, you're going to write things like this in the log. Begin transaction, then whatever changes you make to the database to allow you to recover instead of in case of a crash. And then if you decided to abort transaction. If you decide to commit transaction, right? If you participate in a global protocol, you have to put now entries in the log with respect to what is it that you've done in the global protocol. Okay. So now the coordinator, for example, would need its own log, even if it runs none of the transactions. It needs its own log. And what's going to put in the log is things like this. Write start of two-phase protocol to local log. What I mean by write means it made it to the local storage. It cannot make progress to the next stage until it's sure it made it to the local storage. I want you to understand that, right? Good. By the way, this is one reason why SSD hard drives are extremely good, right? Because you can actually write very fast to them, do and not have to wait too much for this. But it still takes a couple of milliseconds to make sure this happens. What do you do in the meantime? Well, you can run other protocols in parallel, like this. Once you know it made it to the local log, you can vote. You send a vote request to all the participants, right? Actually, you can probably overlap this, right? As long as none of the votes have been collected, you stay and wait for an incoming vote. Imagine implementing this as an actor, right? You just wait for any message from any of the guys, right? If you time out on it, you send the global abort. I'm sorry. You always first write in the log and then do the action, right? So you write the global abort into the local log, and then you send the global abort to all participants. If it made it to the local storage, if you crash, you read the log, you play back the log. I mean, the log navigation strategy depends on what you put in the log and so on. It's a complex business in itself. But when you recover, you're going to look in the log and say, what was I doing at the time? I decided to do a global abort, right? Then you don't know, for example, if the multicast succeeded or not. So when you recover as, for example, the global coordinator, you would send again the global abort, which is always safe because it's idempotent. It doesn't matter if you get it multiple times, right? And then you exit if you decided to global abort in any of them. Right? Otherwise, you record the vote. Now, this is just the first phase. Right? Now, you record the votes. If all the votes are commit, then again, you write the global commit into the log. The moment anything makes it into the log, it's set in stone. So if you crash, you will go and replay that action through this idempotent action mechanism to make sure that that action got through. Now, the other guys could or could not. So if you did crash as a coordinator, the other guys who are in the ready state, they notice that the coordinator doesn't say anything after the timeout. We still have to see the actions. They might have decided on their own to send the commit. And that's fine, because when you send your own version, when you recover, they say, oh, we already committed. But they might, in a rare situation, they might still be stuck in there, and then this is going to unstuck them. Okay? And this turns out to be crucial, because this is, if this guy is missing, the whole system comes to a halt. You cannot make progress with that transaction, right? Again, the moment you see any no vote, you might as well send the abort, and you first, as always, write in the log, then do the action. Right? Now, the participant, what you don't really see here is the actions in the log due to the normal running of the transaction on the side of the participant. You only see the global protocol ones, right? So if you're in the, before you get in the init state, you write init into the local log. Now, it's very important that you use the same log both for the distributed activity and for your own activity. You cannot have more than one log. I mean, it's very, very important, okay? So you write into the log, then you wait for the vote request. If you have a timeout, you vote abort, you vote, I mean, you know you're going to abort, you have to put it in your own local log. Again, you can crash. If you recover, you say, hey, I decided to abort. Now, of course, this vote abort, it has to be paired up with I decided to abort, right? So you say the normal log entry in which you say abort transaction, and the other one is vote abort, right? Now, if you voted commit, you write vote commit in your local log. That doesn't mean you committed. You don't commit. You don't write I committed my transaction. You just write vote commit, and you send your commit. You see, again, write in the log, do the action. If you crash, you can play again the action, right? Then you wait for the decision. If you have a timeout, you have to play this game with let's contact the other participants and see what the decision was, right? You send a decision, you do a multicast with decision request, which means tell me what you voted so that we figure out if we can all commit or abort, right? You wait for the decision, right? And you write the decision in the log. Now, if the decision was a global commit, you commit by writing global commit in the log and then committing. If the decision was global abort, you write global abort in the local log and then you abort. Now, again, if any of these participants crashes and recovers, so don't think that only one guy can crash. In rare situations, multiple participants can crash. You can have a crash of the coordinator and 3 of the participants out of 5. Right? You still have to recover out of everything. So what's unacceptable is to have any of these transaction-like mechanisms that can still get stuck in rare situations. You're not allowed to get stuck. Right? You can delay coming back up because you have to go and play some kind of a crash recovery, but you're not allowed to get stuck. By the way, crash recovery is tricky because you can crash during crash recovery as well. You have to be ready for everything. So, I mean, in the database class, I explained how if you go through the log and you play back the actions during the crash, if you crash, you can still go and fix whatever. You can fix the fixing, right? So all of those are real concerns. Now, by the way, you might say, yeah, but what is the chance? Well, the chance can actually be very high, in fact, because some of the crashes are related to some sort of a hardware defect. It's quite likely that the hardware defect could, in fact, pop up, right? I mean, how many of you, for example, were frustrated with this defragmentation of file systems? By the way, the defragmentation or whatever else activities like that, some kind of a fixing, it's a very sophisticated operation in which you're going and trying to find defects and fix them. But if your machine crashes during that, it could be pretty bad. I mean, Windows was extremely vulnerable at some point to crashes during defragmentation. Even normal file systems, because you maintain linked lists, I mean, there is a special trick, which is a classic trick, for example, in file systems. There is a special trick in which you have to be very careful in what order you do the operations just in case you crash. Because if you don't do them in the correct operation, if you crash, you're simply going to have parts of the storage that nobody knows where they are. Or circular lists, which is worse. I mean, parts that nobody knows where they are is not so bad, because you can do some analysis maybe globally. So being aware of crashes that can happen while you do manipulations of these data structures, right, it's extremely important if you want to have a long-lived system that doesn't crash. OK. OK, so this is how you deal with the decision request. We said here send decision, right? Now, you need to do this in a separate thread, because otherwise you don't make progress, right? So here you say you wait until decision is received, but you're part of the decision making also. So you need, I mean, with actors it's very easy, right? You maybe spawn another actor that takes care of this. Notice that you're not getting here for the most part. If the algorithm runs OK, you're not going to get into this business of talk to the other participants, right? You're just working as normally. So the standard scenario you can think about is you're going to do millions to billions of normal transactions before one of them is damaged. But you have to be ready for the damaged one, not to have the system getting stuck, right? So in a separate thread, you can do this, right? While true, you wait for incoming decision request, right? You look at the most recent recorded state from the local log. Now, you do this just in case you crashed, OK? And if the state was a global commit, you say, hey, I know of a global commit we all must commit. If the state was init or a global abort, you say, we abort. Okay? Otherwise, you just stay in there, because, I mean, it's a separate thread, and this is a mechanism rarely used. Okay? So let's look at the picture again. If you're still in the init state, it's safe to say abort. Again, the aborts are safe. Right? I'm not going to go into all the details in this class, because, I mean, you can't teach everything in a single class. But aborting transactions is one of the main mechanisms to get out of trouble in a transactional system, right? For example, a lot of the optimistic concurrency control mechanisms work like this, right? You say, I'm going to optimistically assume that there is no interference with me. But if I detect interference, I, in fact, have to abort the transaction, which is equivalent to a rollback, right? As long as you don't do it too often, that's a perfectly fine mechanism to do things. Right? Or, for example, another one is you use locks in order to correctly run transactions. If you have a deadlock, you have to abort one of the transactions and release the locks of the transaction, because otherwise you're never, I mean, you get the whole system stuck. So, I mean, you can do aborts for strange reasons, right? Including deadlocks and whatnot. OK, good. I don't expect you to remember all the details in the protocol, but I want you to have an idea about what two-phase commit is all about. Now, what's three-phase commit all about? Well, in two-phase commit, you still have to do this voting, and on rare occasions, you have to wait for the global coordinator to recover, right? Even in situations when a decision could have been reached, and that's the problem, right? So if you have too much waiting going on beyond the normal wait in which everybody has to finish their own transaction, that's potentially not good. This is why the free-phase commit was proposed together with other kinds of algorithms. Now, again, even before I tell you this, it's my duty to tell you that it's really not used in practice. It's a very nice academic protocol. You almost surely will be asked about the free-phase commit, because it's a favorite question by any interviewer, right? You say, hey, you took the distributed systems, what's free-phase commit, right? Or what's the difference between two-phase commit? It's one of those easy questions in an interview, but reasonably irrelevant in practice, right? But nevertheless, you're going to be asked about this. It's like normalization in database. Right? You just get questions about it. It was third normal form, which nobody uses, versus the BCNF. Anyway, all right, good. So the three-phase commit, it's relatively an academic issue, was introduced to make sure nobody is ever stuck, and you can actually make safe progress. So you can decide whether you do an abort or you do a commit, even in the presence of the global coordinator failure, right? And in particular, you don't have to wait for the global coordinator's recovery to finish, in case that's the only thing that actually happened. Okay? And these are two assumptions that need to be true for the two-phase commit to actually run well. I'm not even going to go into them. They look reasonably esoteric. Okay? So here's the difference, okay, in the three-phase commit versus two-phase commit. I mean, as the name suggests, there is another phase. So the other phase is this pre-commit. So the global coordinator is going to do this. Init, wait, it's exactly the same as before. And then it's going to send the, so right in between it sends the vote request. But here's the difference. If it gets any single abort, it's going to say abort, and everybody aborts. That's fine. But if it gets a commit, it's not going to send a global commit. It's going to send something called prepare commit. And it makes the transition to a state called pre-commit. Only when it gets acknowledgments for all the pre-commits, it's going to go and say commit. Okay? So let's see how this helps. Okay? So this is from the participant point of view. Again, init, ready, I get the vote, I send abort or commit. I said abort, I might as well abort. Now, of course, if a single abort is received, you go on this path, and everybody will find that it's an abort. Okay? If you send a commit, and you got the message prepare commit, you yourself get in the state pre-commit. And you're waiting for this global commit. Now, of course, the question is, if that global commit doesn't come within the timeout, what could you possibly do? Now, here's a number of key observations on this. Okay? Namely, if you got a pre-commit as a participant, you know for sure that everybody, in fact, got to the ready state. Namely, they were ready to commit. And in fact, internally, they decided they can actually commit. Right? It's not possible to get the pre-commit until this guy gathers all the votes. And if he got all the votes, that means everybody said commit. Okay? Now, it's still not clear if you can go on and commit your stuff, because you have to make sure if you commit that even in the presence of crashed participants, when they recover, they figure out that it was a commit and go and commit. Okay? So it's safe to commit only when you know for sure, not only that, I mean, it doesn't have to be the case that now the guys decided that it's a commit, but if they recover and they finish the protocol, they decide it's a commit, and there's no way to do an abort. Okay? All right. So normal functioning, you send the pre-commit. Everybody gets the pre-commit, they do it, okay, fine, it's done. You have this extra message though, right? So before you send vote and you gather all the votes with unicast. Now you say pre-commit and you get all the X for pre-commit. So you need extra messages, not only you need one extra multicast and one wave of acknowledgements from the multicast in order to issue the commit. Now, what could possibly happen if you got in the pre-commit and you detect that the coordinator actually died? Well, again, you can go and contact the other participants into the protocol, right? And as long as you can determine just by the fact that you got into the pre-commit that you can go and commit, you can actually avoid waiting for the coordinator. So the trick is going to be, could we decide for sure that we can commit based on the state without waiting for this guy to recover safely, always? Let me see what slides I have. Okay, this is basically another issue. And I have about 12 minutes, right? So it turns out that things do become a lot easier. They become a lot easier, again, because you can tell for sure if you got to pre-commit that nobody is in the init state, and you know that everybody does logging locally, right? So, for example, if you got a single, how does this work? Right, so you got the pre-commit, you contact other guys that actually got the pre-commit. You know that the existence of the pre-commit means you can actually issue a global commit yourself as a participant. You don't have to wait for this guy. Anybody issuing a correct global commit means the transaction committed, and the other guys are just going to, I'm sorry. If this guy sent the pre-commit, he wrote in its own log, I pre-committed, And knowing that what these guys are actually going to do, namely somebody's going to finish the transaction, it knows that it doesn't even need to send the global commit. And to that extent, any of these guys could send the global commit and actually finish the transaction. So when this guy recovers, it's going to say, hey, I sent the pre-commit, fine. I can just consider the transaction to be finished, even though I actually crashed in the middle of it, right? The trick here is to figure out if it's possible in the presence of failures of now both coordinators and participants that if you can run in trouble. So the kind of trouble you can have is the following. Some participants get the pre-commit and some participants don't get the pre-commit, right? Now that's possible because the global coordinator got the pre-commit and does the multicast. It's the same problem as before. Got the pre-commit and does the multicast. It could have crashed in the middle of doing the multicast, or for some of them the message didn't go all the way through, or whatever else happened, right? So in the process of contacting now all the other sites as it happened before, you can actually apply the following technique. As long as all these guys, by the way, agree to abort, that's still an option. So when you run the protocol, you go and count how many pre-commits you got. If you get a majority vote for the pre-commit, you know for sure that you can safely commit because nobody else can get a majority vote to decide to actually abort. Not only you're going to do this, but you're going to broadcast. Once you got enough votes, you're going to broadcast the global commit. If you have a timeout and nobody managed to get at least half the votes, then each of the guys independently is going to say, we ran out of time and we can actually abort. Okay? So you still keep an abort as an option, but the majority vote here allows you to bypass completely the coordinator. In particular, don't have to wait for the coordinator to come back. Assume again that a crash is much more expensive than the timeouts in the protocol. Okay? All right. Again, mostly academic issue. The extra thing you have is a pre-commit phase that allows you to do voting to determine what actually happened and what not. Now, I have 9 minutes left. Let me talk about high-level issues related to state recovery in general. Okay? Now, we talked about stable storage. Stable storage, it's again, you wrote something on the disk, so if you crash, you can go back and see what was on the disk. We have now the SSDs, right? They don't need power to remember the information. Now, you still want to have redundancy in the overall system in case the whole thing crashes and burns, right? But from the point of view of maintaining continuity for the transaction processing at one site, you need this kind of stable storage. Very tricky techniques to implement it right. For example, just to mention one, even when you write on hard drives, so for example, you make a request and you say, write this. You're low in the operating system, not a high-level function. You say, write this on the disk. But how do you know it actually makes it to the disk? Especially, how do you know it makes it completely to the disk? Maybe part of the information made it, part of the information didn't make it. So how do you really, really know? Well, you can't really, really know. So this is why, for example, they sell you something that might look like it's crazy. Why would I do that? They sell you battery packs for the RAID card. So what that is, it's a battery system that will keep the RAID card alive for a couple of tens of milliseconds to make sure that any such request to write something on the hard drive actually completes and you actually write on the hard drive. Okay? So that's when you get into the so-called enterprise hardware. So really the difference between consumer hardware and enterprise hardware is detect more failures in hardware and have ways to mitigate some of this partial failure. So when the power goes down, it doesn't just go down. There is no such thing as instantaneously the power go down. There is about a millisecond or 2 milliseconds left of some power because of the way the power supply is implemented and so on. But you want to make sure that everybody can just push that one last request. Okay? And battery packs for RAID cards are especially introduced to be able to know for sure that the entry in the log made it all the way to the disk safely. Okay? Okay, I'm not going to go through all of these things. All kinds of techniques I use with checksums and whatnot. Okay, the big issue I just want to brush upon a little bit is checkpointing. Right? So what's this checkpointing in general? Checkpointing refers to take a snapshot of the current state in case something completely gets destroyed. It's a safe place to come back to and know what the state was. Now that's needed anyway when you have log-based recovery, because otherwise you in fact have to play the log from the beginning of time. Okay, so you see the log contains all the sequence of actions that you in fact have done. So that's fine. But what are you going to do? Play the log from the beginning and start with a completely, for example, completely empty database and then play the log in order to do all the actions that you were doing? Now, you could do that. It might take a couple of weeks to play back all the transactions. That would be a complete disaster. So the secret with recovery is to do it fast enough. Because if the recovery process takes a long time, for example, this happens with the RAID controllers, right? You have redundancy in a RAID controller, but it might take you 10 hours to recover a correct state of the hard drives in the presence of failure using the redundancy, then you're not making much progress. So the checkpointing is a safe point where you can roll back things, and from that moment on you can play, for example, the log in order to recover the most recent state. Okay? Now checkpointing can be used in many other roles. For example, when you do a very long, complex computation, if you do checkpointing in case you have some defect of any sort in your software, you could recover the state as of 10 minutes ago and only lose 10 minutes of work as opposed to 3 weeks of work or 1 year of work. I mean, some people have computations that go on for 1 year, right? So it's a technique used all over the place. But checkpointing is hard enough on a single machine because you have multi-threading and whatnot, and it's quite complex. Think about your actors, right? Your actors have state. How would you capture the state of all the actors at the same time, given the fact that they run in multiple threads? Well, one way to do it, for example, is to freeze the threads, go and chase down the state for everybody, write it on the disk, and then unfreeze the threads. But that means you're not doing anything while you're checkpointing. So it gets very tricky. And this is why it's an extremely research topic. It's how can you do if they have something called incremental checkpoints, right, in which you do a begin checkpoint, you're still doing whatever normal thing, and then you have an end checkpoint, and you can crash or not crash during checkpoint. Of course, if you do the checkpoint, it's invalid. But if you don't crash, you still can recover and do things. It can get very, very complex. Now, there is another layer of complexity when it comes to checkpointing when you do distributed checkpoints, right? So especially when you do a computation, for example, across multiple machines, and they have all these messages going in between them to do all kinds of stuff, you, in fact, want to get a snapshot across all the systems, not only a snapshot on this local machine. Good snapshots on the local machine do not guarantee a good snapshot overall, right? So the trouble overall is you send a message saying do this action. But if you crashed and you don't recover a state in which the message was sent, you can run into situations in which one side got a message and you never know that you send the message. Right? Now that might or might not be a problem for your application, but you can easily see that there are situations in which it is. So then you can tackle this extremely hard problem, which is this global snapshot, and it's relatively nasty. Now, one safe to do it would be you're going to go and write on local checkpoints and make sure that each of the checkpoints, in fact, reflects messages that were sent in between. And if they don't, roll back even in between checkpoints. So this is called the domino effect. So in fact, what you could end up with is, even though you have lots and lots and lots of checkpoints, you have to go back many hundreds of checkpoints until you recover a state in which you know for sure what actually happened. Right? So it's, again, a matter of trading safety for performance. All right? Or you can do what Amazon does and design the system so you don't care what goes on, and it's kind of OK. Right? As long as it's not financial stuff. Right? So really, the big challenge when it comes to fault tolerance is how not to overdo it, right? You can always design things that are very sturdy, but then potentially they have a big performance penalty. If something goes wrong, you might have to stay there for weeks to recover the state, and that's not good in itself. Or you can give up some of the promises, give up some of the things, and simply have a more relaxed model. And this is why designing custom solutions is a very viable and desirable thing to do, for example, for a large company like any of these big, large companies like Amazon and so on, right? So it's nice to say, hey, we're going to build some kind of libraries and everybody uses the libraries, but because in distributed systems, so many things can be dialed in. I can trade this for that and this for that. You can go on and say, you know what, I'm going to design my own version of this because I have a different trade-off that's relevant for me. That explains why you have so many projects all over the place. I mean, every large company has its own way of doing some of these things, and that's kind of the reality, right? As opposed to canned solutions, let's say. Okay? All right, so that's all I wanted to say about fault tolerance. We're going to have a quiz about this. I'm going to ask you about two-phase commit and three-phase commit and this and that and whatnot, and then we are done, right? And in fact, what you're doing in your project can be viewed as some kind of a logging that could be used even for recovery, right? If you write enough information in that log that you're going to analyze to see what happened when you have bugs, you can, in fact, implement, okay, this, I don't know, actors died, we can recover the state of the actors, especially if you add some kind of checkpoint into the middle. So to some extent, it does even more than what you might think it does. And of course, the log can be consulted to even figure out if something ran amok. Right? When we talk about security, the security log, which is going to be similar to this, can actually be audited to see who was the person that accessed what they shouldn't have accessed and how, like Snowden. Right? Anyway. All right, good. Focus on the project and tackle part 2 simultaneously with part 1. That's my advice. Right? Don't just give me a simple thing and so on. Give me your best shot at the part 2. All right. I'll see you Tuesday.